Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Waves. Waves transfer energy without transferring matter. Waves are classified into two types: transverse waves and longitudinal waves. Transverse waves. In transverse waves, the direction of vibration is perpendicular to the direction of propagation, or direction of energy transfer, or the direction of wave traveled. For example, water waves, seismic secondary waves, slinky waves and electromagnetic waves. We can demonstrate the transverse wave by shaking the spring up and down, as shown. Direction of vibration is up and down, which is perpendicular to the direction of wave propagation, or direction of energy transfer, or direction of wave traveled, is to the right. Direction of vibration is up and down, around the equilibrium position. This is the equilibrium position. When the wave vibrates for one cycle, it creates one wave that travels one wavelength. The red particle at the red arrow is moving up and down. This shows that wave transfers energy without transferring matter. Highest peak is called a crest. Lowest peak is called a trough. Longitudinal waves. In longitudinal waves, the direction of vibration is parallel to the direction of propagation, or direction of energy transfer, or the direction of wave traveled. For example, sound waves, slinky waves and seismic primary waves. We can demonstrate a longitudinal wave by shaking the spring forward and backward, as shown. Direction of vibration is forward and backward, which is perpendicular to the direction of wave propagation, or direction of energy transfer, or direction of wave traveled, is to the right. Direction of vibration is forward and backward, around the equilibrium position. This is the equilibrium position. When wave vibrate for one cycle, it creates one wave that travels one wavelength. Where the spring compresses together, this is called a compression. Where the spring extends apart, this is called a rarefaction. Compression is where wave particles are close together and high pressure, or high density. Rarefaction is where wave particles are far apart and low pressure, or low density. Describing waves. Here is the graphs of displacement time graph of a traveling wave. Here is the displacement distance traveled graph of a traveling wave. Amplitude, A, of a wave is the distance from equilibrium position to the peak of the wave. It represents energy carried by the wave, so a wave with a high amplitude carries a lot of energy. Wavelength, lambda, of a wave is the distance between consecutive peaks, or between consecutive identical points. It is measured in meters, m. Frequency, f, of a wave is the number of vibrations per second or numbers of waves that travel past a point per second. It is measured in hertz Hz. Period, t, of a wave is the time taken for one vibration to completely or for one wave to travel past a point. It is measured in seconds, s. If a water wave travels n waves in t seconds, its frequency is n to divide by t. Its period is t to divide by n. So, frequency is 1 to divide by period. Speed, v, of a wave is the distance traveled by wavefront per unit time. It is measured in meters per second. If the distance traveled is one wavelength, then the time taken is one period. Since 1 over period is equal to frequency, then speed is equal to wavelength times frequency. Wavefronts of wave are the lines along peaks, compressions, or rarefactions of the wave are aligned. Demonstrating the wavefronts of the water wave in a ripple tank. A ripple tank is a shallow tray of water, with a light source shining down through it. The light illuminates the wavefronts, making them visible. A straight dipper can be used to create straight wavefronts in a ripple tank. When the dipper is vibrated up and down, It creates a series of parallel wave fronts. The screen below the ripple tank is used to observe the wave fronts of the water wave. The stroboscope, or video camera, is used to make the slow motion of the wave fronts of water wave on the screen. A small sphere dipper can be used to create circular wave fronts in a ripple tank. When the dipper is dropped into the water, it creates a circular wavefront that expands outward, as shown. The side view of the water wave in the ripple tank. The top view of the water wave in the ripple tank. We see the wavefronts are straight along crests, or troughs of the wave. So, the distance between consecutive wavefronts is wavelengths. Because of the wavelength, is the distance between two consecutive crests, or troughs of the wave. The direction of propagation, or direction of energy transfer, or direction of wave traveled, is always perpendicular to the wavefronts. Reflection of waves. When waves hit an obstacle, they are reflected. The direction of the wave propagation changes, but the speed, wavelength, and frequency remain constant. Demonstration of wave reflection using a ripple tank. The incident wavefront hits the obstacle, creating the reflected wavefront, as shown. When the series of incident wavefronts hit the obstacle, creating the series of reflected wavefronts, as shown. Candidates should be able to draw the diagram of this reflection. Draw the incident wavefronts and the reflected wavefronts. The angle between the incident wavefronts and the surface of obstacle is equal to the angle between the reflected wavefronts and the surface of obstacle. Draw the incident ray that is perpendicular to the incident wavefronts, and its direction is the direction of wave propagation, direction of energy transfer. Draw the normal line at right angle to the surface of the obstacle. The angle of incidence, I, is between the incident ray and normal line. Draw the reflective ray that is perpendicular to the reflected wavefronts, and its direction is the direction of wave propagation, direction of energy transfer. The angle of refraction, R, is between the reflective ray and normal line. Space between consecutive wavefronts is wavelength, which are equal before and after reflection. Rules of the reflection. The angle of incidence, I, is equal to the angle of reflection, R. The incident ray, reflective ray, and normal lie on the same plane. Circular wavefronts can be reflected at a flat obstacle, as shown. The circular wavefronts is created from source, S. They reflect at the flat obstacle. The image of the source, R, is created behind the obstacle, which the reflected waves appear to come. Refraction of waves. When waves travel through one medium to another, they are refracted. This is because the speed of wave is changed, causing its wavelength also change, while its frequency remain constant. Demonstration of wave refraction using a ripple tank. This area is shallow water and this area is deep water. In a shallow water, place the glass block in the water. The water waves travel slow in shallow water due to the friction increase, so its wavelength also decreases, while constant frequency. The water travel fast in deep water due to the friction decrease, so its wavelength increases, while constant frequency. The incident wave fronts travel from deep water to shallow water. The wave speed decreases to cause the wave fronts bend toward the normal line, and they are close together. This causes the wavelength to decrease. Candidates should able to draw the diagram of the refraction of wave. This is the boundary between shallow and deep water. This region is deep water. This region is shallow water. Draw the incident wave fronts of wave in deep water. Draw the refractive wave fronts of wave in shallow water. Draw the direction of incident ray at perpendicular to the incident wave fronts. Draw the normal line at perpendicular to the surface of the boundary. Draw the refractive ray at perpendicular to the refracted wave fronts. The angle of incidence, I, is between the incident ray and normal line. The angle of refraction, r, is between the refractive ray and normal line. When the water wave travel from deep water to shallow water at perpendicular to the surface of boundary as shown. This region is shallow water. This region is deep water. The wave fronts are not bent, but the wave fronts are close together. This shows that wavelength decreases due to the wave speed decreases when travel from deep to shallow water. Draw the diagram to show the refraction of wave of this situation. This region is deep water. This region is shallow water. Draw the incident wave fronts of wave in deep water. Draw the refractive wave fronts of wave in shallow water. Draw the direction of incident ray at perpendicular to the incident wave fronts. Draw the normal line at perpendicular to the surface of the boundary. Draw the refractive ray at perpendicular to the refracted wave fronts. The angle of incidence is between the incident ray and normal line to be 0. The angle of refraction is between the refractive ray and normal line to be 0. Therefore, the refractive ray is not bent when the incident ray travels along the normal or perpendicular to the boundary. This is because the angle of incidence and angle of refractive are equal to 0. Doppler effect. When a stationary ambulance car emits sound waves, the wave fronts spread out symmetrically, forming circles around the source. If the wave source moves, the waves can become compressed in front of it and stretched behind it. This movement changes the wavelength and frequency of the waves. In front of the source, the wavelength decreases and the frequency increases. Person A hears sound that has a higher pitch than when the car was stationary. Behind the source, the wavelength increases and the frequency decreases. So person B hears a sound with a lower pitch than when the car was stationary. These apparent changes in frequency, which occur when a source of waves is moving, is called the Doppler effect and is a property of all waves. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Electromagnetic spectrum. All electromagnetic waves have the following properties. They are all transverse waves. They can all travel through a vacuum. They all travel at the same speed in a vacuum. Its speed in a vacuum is 3 times 10 to the power of 8 meters per second and is approximately the same in air. The electromagnetic spectrum is arranged in a specific order based on the wavelengths or frequencies. The main groupings of the continuous electromagnetic spectrum are radio waves, microwaves, infrared, visible light, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-rays, gamma rays. This order is shown in the diagram from longest wavelength to shortest wavelength, lowest frequency to highest frequency, lowest energy to highest energy. Size of wavelength of radio wave is approximately to the size of the building. Microwave is approximately to the size of baseball. Infrared is approximately to the size of pinpoint. Visible light is approximately to size of the bacterial. Ultraviolet is approximately to size of virus. X-rays is approximately to size of atom. Gamma rays is approximately to size of subatomic particles. The higher the frequency, the higher the energy of the electromagnetic waves. Electromagnetic wave with higher energy is highly ionizing, harmful to cells and tissues causing cancer, such as UV, X-rays, and gamma rays. Electromagnetic wave with lower energy is less ionizing, less harmful to humans, such as radio waves, microwaves, infrared and visible light. Useful for communications. Uses of electromagnetic waves. Electromagnetic waves have a variety of uses and applications. Radio waves. Communication. Radio waves are used to transmit the signal of radio and television. They are also used in cellular networks, GPS, and Wi-Fi. Radio frequency identification uses radio waves to identify people or objects. They are used in a variety of applications, such as inventory tracking, access control, and payment systems. Bluetooth is used to communicate between two Bluetooth-compatible devices. Astronomy. Radio telescopes are used to observe the naturally occurring radio waves that come from stars, planets, galaxies, and other astronomical objects. Microwaves. Communication. Microwaves are used to transmit the signal of satellites, television, and mobile phones. They are also used in radar systems. Cooking. Microwaves are used to heat food in microwave ovens. They work by causing the water molecules in food to vibrate, which creates heat. Infrared is emitted by warm objects. Electric grills. Some electric grills use infrared heat to cook food. Remote controls. Remote controls use infrared light to send signals to devices such as TV. Intruder alarms are the motion sensor. Thermal imaging. Infrared cameras can be used to create images of objects that emit infrared radiation. This can be used for medical imaging, security, and industrial applications. Optical fibres. Optical fibres are used to transmit the signal in the communication, which is more efficiently than visible light. Visible light. Seeing. Visible light is the part of the electromagnetic spectrum that can be detected by the human eye. It is used for vision, photography, and videography. Communication. Visible light can be used to transmit data in optical fibers. Ultraviolet. Fluorescence. Some substances glow when they are exposed to ultraviolet light. This can be used to create security markings and detect fake banknotes. Tanning. Ultraviolet light from the sun can cause tanning. It can also cause skin cancer. Sterilization. Ultraviolet light can be used to sterilize surfaces and kill bacteria. It is used in hospitals, laboratories, and food processing plants. X-rays. Medical imaging. X-rays are used to create images of the inside of the body. They are used to diagnose diseases and injuries. Security scanning. X-rays are used to scan luggage and people at airports and other security checkpoints. Gamma rays. Sterilizing food and medical equipment. Gamma rays can be used to bacteria and living things. Cancer treatment. Gamma rays are used to kill cancer cells. Harmful effects of electromagnetic waves on people. The higher the frequency of an electromagnetic wave, the higher its energy. Electromagnetic wave with higher energy is more ionizing, meaning that it can remove electrons from atoms or molecules. This can be harmful to cells and tissues, and can even cause cancer. Electromagnetic wave with lower energy is less ionizing and is less harmful to humans. It can still be harmful, however, if it is absorbed in large amounts. Beyond the visible part of the spectrum, the energy becomes large enough to ionize atoms. The main risks associated with electromagnetic waves are summarized as: radio waves, no known danger; microwave, possible heat damage to internal organs, when the water molecules in the body absorb microwaves strongly; infrared, infrared can cause heating effects in tissues, meaning it can also cause skin burns, but it is less likely to cause internal damage than microwaves. Visible light. Very bright light can cause eye damage. This is because the retina of the eye is sensitive to light. Ultraviolet. If eyes are exposed to high levels of UV, it can cause severe eye damage. Skin cancer. Ultraviolet is ionizing, meaning it can kill cells or cause them to malfunction, resulting in premature aging and diseases such as skin cancer. X-rays. X-rays are the most ionizing radiation, meaning they are able to penetrate the body and cause internal damage, so they are caused to kill cells, mutation of genes, and cancer. Gamma rays. The harmful effects of gamma rays like as X-rays, because they are the most ionizing radiation, so they are caused to kill cells, mutation of genes, and cancer. It is important to note that the harmful effects of electromagnetic waves depend on the amount of radiation that is absorbed. A small amount of radiation may not be harmful, but a large amount of radiation can be very harmful. The risk of harm also depends on the type of tissue that is exposed to the radiation. For example, the retina of the eye is more sensitive to light than other tissues, so it is more likely to be damaged by exposure to visible light. The best way to protect yourself from the harmful effects of electromagnetic waves is to limit your exposure. This means avoiding using electronic devices for long periods of time, staying away from sources of strong radiation, and wearing protective clothing when necessary. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. General properties of light waves. Light waves are the transverse waves and electromagnetic waves, so light can transfer energy through the vacuum. Speed of light in the vacuum is 3 times 10 to the power of 8 meters per second, which is approximately equal to speed of light in air. Light is travel in the straight line. Light wave exhibits the refraction and refraction. Reflection of light on plane mirror. When a ray of light strikes a plane, flat, mirror, it is reflected so that the angle of incidence, I, is equal to the angle of reflection, R. Mirrors are often used to change the direction of a ray of light, while its speed, frequency, and wavelength remain constant. The normal is a line at right angles to the mirror. The angle of incidence is the angle between the incident ray and the normal. The angle of reflection is the angle between the reflected ray and the normal. Therefore, the rule of reflection R. Angle of incidence, I, equals angle of reflection, R. The incident ray, reflective ray, and normal line lie on the same plane. Periscope consists of 2 plane mirrors. It is one example that uses 2 mirrors to change the direction of rays of light. Rays from the object strike the first mirror at an angle of 45 degrees to the normal. The rays are reflected at 45 degrees to the normal, and so are turned through an angle of 90 degrees by the mirror. At the second mirror, the rays are again turned through 90 degrees. Changing the direction of rays of light in this way allows an observer to use a periscope to see over or around objects. Refraction of light. Light will refract when it travels through the transparent materials, such as glass. Angle of incidence is denoted by I. Angle of refraction is denoted by R. As the incident light ray enters the glass block, it slows down and bends towards the normal. As the light ray leaves the glass block, it speeds up and bends away from the normal. The frequency of light is unchanged as it travels from one medium to another. The wavelength of light changes directly with the speed of light. As the light speeds up, the wavelength increases. As the light slows down, the wavelength decreases. When light travels from an optically less dense medium to a more dense medium, it slows down and so bends towards the normal. When light travels from a more dense to less dense medium, it speeds up and bends away from the normal. If the angle of incidence is 0 degrees, the ray enters along the normal to the surface of the glass block. The light slows down but does not change direction, because the angle of refraction is also 0. As it leaves, it speeds up, but does not change direction. Refractive index. Different materials can bend rays of light by different amounts. We describe this by using a number called the refractive index, n. Refractive index, n, of a material, medium, is the ratio of sin I and sin r. We can use the equation below to calculate the refractive index of a material. N equals sin I over sin r, where I is the angle of incidence. R is the angle of refraction. N is the refractive index, it have no unit. The refractive index in air is approximately equal to 1. In figure as shown, we can find the refractive index of medium A using the following equation as shown. Substitute I equals 50 degrees and R equals 40 degrees. The results of N is 1.2. We can find the refractive index of medium B using the same following equation as shown. Substitute I equals 50 degrees and R equals 30 degrees. The results of N is 1.5. From the results of example, we can see that light bends in medium A less than the medium B. So, light refracts in the medium A less than in the medium B. And the refractive index of medium A is less than the medium B. This shows that the density of medium A also less than the density of medium B. An experiment to investigate the refractive index of glass. Place a glass block on a piece of paper, and trace around the block with a pencil. Shine a ray of light in air on the glass block. Place 2 pins along the incident ray, with a separation of more than 5 centimeters, to ensure accuracy when drawing the line. Place 2 pins along the emerging ray from other side of glass block, with a separation of more than 5 centimeters. Remove the glass block and pins, then mark at the pins holes. Turn off the light box. Use a ruler to draw the incident ray and the emerging ray. Then, connect the entry and exit points to show the path of light within the glass block. Draw the normal line at the point of incidence. Measure the angle of incidence, I, and the angle of refraction, r. Calculate the refractive index of the glass using N equals sin I over sin r. The critical angle and the total internal reflection in a medium. As the rays shine on the semicircle glass block, the light slows down but does not change direction. This is because the angle of incidence is 0 degrees, the ray enters along the normal to the surface of the glass block, then the angle of refraction is also 0. As the ray reach the point A, some ray reflect and some ray refract. When a ray of light travels from a denser medium, glass, to a less dense medium, air, it bends away from the normal. As the angle of incidence, I, increases, the angle of refraction, r, increases. The intensity of refractive ray decreases, while intensity of reflective ray increases. When r equals 90 degrees, the angle of incidence is equal to the critical angle, c. Therefore, the critical angle is the angle of incidence in denser medium, where the angle of refraction is 90 degrees. We can calculate the critical angle using the equation sin of c equals 1 over n. If the angle of incidence is increased beyond the critical angle, total internal reflection occurs. The total internal reflection occurs when the light ray travels from denser medium to less dense medium. The angle of incidence is more than the critical angle of the medium. No refraction of light. The angle of incidence is equal to the angle of reflection. Uses of the total internal reflection in everyday life. Periscope consists of the glass prisms, which are used in submarines. As a light ray travels through a periscope, total internal reflection occurs at point A and point B. A glass right-angle prism with an angle 45 degrees. The critical angle of glass is about to 42 degrees. As the light ray travels from air to glass at the angle of incidence is 0, so the light slows down, but does not change direction. The light ray reflects at the point A with the incident angle of 45 degrees, which is greater than the critical angle of glass, 43 degrees. This causes the light ray to undergo total internal reflection. As it leaves the prism, it speeds up, but does not change direction. Binocular consists of the prisms as shown. As the light ray travels through a binocular, and the total internal reflection occurs at points A, B, C and D. The prisms in this binocular are glass right-angle prism 45 degrees. As the light ray travels from air to glass at the angle of incidence of 0, so the light slows down, but does not change direction. The light ray reflect at the point A with the angle of incidence is 45 degrees, which is greater than the critical angle of glass. This causes the total internal reflection to occur. Then the light ray reflect at the point B with the angle of incidence is 45 degrees, which is greater the critical angle of glass. This causes the total internal reflection to occur again. As it leaves from the prism, it speeds up, but does not change direction. Rear reflector. Rear reflectors use total internal reflection to reflect light back to the source. They are often used on vehicles to improve their visibility to other road users. Optical fibres. An optical fiber is a thin glass cylindrical core coated with a transparent material of lower refractive index cladding. The cladding has a lower refractive index than the core, so it is less dense. This means that total internal reflection will occur for all rays of light that strike the boundary between the core and cladding at an angle greater than the critical angle. Optical fibers can be used to communicate signals, for example telephone conversations, or in medical applications, such as endoscopy, a method of examining inside the body. In the communications, optical fibers are used in the TV, internet, and phones. Light or infrared carries the information along the optical fibers. They can carry a large amount of information at very high speed. In medicine, optical fibers are used in the endoscopes that allow the surgeons to see inside the body of their patients. Light ray from the outside is transmitted through the optical fibers and undergo total internal reflection, which prevents them from leaving the optical fibers. Light ray reflected at the inside the body and return back to the outside along the other optical fibers. This light is sent to the computer monitor. Describing sound wave. Sound wave is the longitudinal wave, which means that the particles of the medium vibrate in the same direction as the wave is traveling. Sound waves are produced by vibrating sources. When a vibrating source moves back and forth, it creates pressure variations in the surrounding medium. Sound waves require a medium to transfer their energy. The medium can be air, water, or any other solid or liquid. This is why sound cannot travel through a vacuum. The sound travels faster in solids than in liquids, and faster in liquids than in gases. The speed of sound in air is approximately to 330 meters per second. The speed of sound in liquids is approximately to 1,500 meters per second. The speed of sound in solids is approximately to 300 to 500 meters per second. The explanation of how a source, such as a drum, produces sound. When you bang a drum, the skin vibrates. The vibrating drum skin causes nearby air molecules to vibrate. This is because the air molecules are bumping into each other. The vibrating air molecules cause other nearby air molecules to vibrate, and so on. This creates a series of compressions and rarefactions in the air. The compressions are regions where the air molecules are closer together and high pressure. The rarefactions are regions where the air molecules are farther apart and low pressure. The compressions and rarefactions travel through the air as sound waves. The distance between the consecutive compressions or consecutive rarefactions is the wavelength. The harder you bang, the bigger the vibrations and the louder the sound. This causes the air molecules to be closer together in the compressions and farther apart in the rarefactions. The greater the difference between the air pressure in the compressions and rarefactions, the louder the sound. An experiment to determine the speed of sound in air. The speed of sound in air is approximately 330 meters per second at 25 Celsius. Speed of sound in the hot air is faster than in the cold air. This is because the air particles in hot air have higher speed than the cold air. So, the speed of sound in air varies from 330 to 350 meters per second. Investigate the speed of sound between 2 points. Two people stand a distance of around 100 meters apart. The distance between them is measured using a tape measure. One person has two wooden blocks, which they bang together. The second person has a stopwatch, which they start when they see the first person banging the blocks together, and stops when they hear the sound. This is then repeated several times, and an average value is taken for the time. The speed of sound can then be calculated using the equation. Speed is equal to the distance traveled by sound to divide by time taken. Reflection of sound. Sound waves behave in the same way as any other wave. When a sound wave from a turning fork strikes a surface, it may be reflected. Like light waves, sound waves are reflected from a surface so that the angle of incidence is equal to the angle of reflection. The speed, frequency, and wavelength of the sound remain constant. The reflection of sound causes echo. Sonar and the echo sounding can be used to measure depth or to detect objects underwater. A sound wave can be transmitted from the surface of the water. The sound wave is reflected off the bottom of the ocean. The time it takes for the sound wave to return is used to calculate the depth of the water. The distance the wave travels is twice the depth of the ocean. This is the distance to the ocean floor plus the distance for the wave to return. The depth of the water can then be calculated using the equation. Speed equals the twice of the depth to divide the echo time. Investigate the speed of sound using the echoes of sound. The echoes of sound is caused by the reflection of sound. A person stands about 50 m away from a wall using a tape measure to measure this distance. The person claps two wooden blocks together and listens for the echo. A second person has a stopwatch and starts timing when they hear one of the claps and stops timing when they hear the echo. The process is then repeated 5 times and an average time calculated. The distance traveled by the sound between each clap and echo will be 2 times 50 meters. The speed of sound can be calculated from this distance and the time using the equation. Speed is equal to the twice of distance to the wall and divide by echo time. The echo time is time that the sound travels forward and backwards. Refraction of sound waves. All waves can be refracted, even sound waves. For example, if some parts of a sound wave are traveling through warm air, they will travel more quickly than those parts traveling through cooler air. As a result, the direction of the sound wave will change. It will be refracted. Although it is not possible to see sound waves being refracted, we can sometimes hear their effect. If a person A is standing at the edge of a large pond or lake, he can sometimes hear sounds from person B on the other side of the water much more clearly than we would expect. This is due to refraction. In figure explains how this happens. Most of the sound person B here travels to us in a straight line, path B. But some sound travels upwards, path A. If the temperature conditions are right as shown, which usually happens in nighttime, some parts of a sound wave are traveling through warm air, they will travel more quickly than those parts traveling through cooler air. Then as the sound waves travel through the air, they are refracted and follow a curved path downwards, path C. Pearson now receive two sets of sound waves. So, the sound Pearson B here seems louder and clearer. Pitch and frequency of sound. The frequency of a sound wave is related to its pitch. Sounds with a low pitch have a low frequency, or long wavelength. Sounds with a high pitch have a high frequency, or short wavelength. Loudness and amplitude of sound. The amplitude of a sound wave is related to its volume. Sounds with a large amplitude have a high volume. Sounds with a small amplitude have a low volume. Audible range. Humans can hear sounds between about 20 Hz and 20,000 Hz in frequency, although this range decreases with age. The sound with frequency higher than 20,000 Hz is called ultrasound, which is beyond the range of human hearing. The sound with frequency lower than 20 Hz is called the infrasound. Investigate the speed frequency of sound using the oscilloscope. Although we cannot see an actual sound wave, we can see an image or representation of it by connecting a microphone to a piece of apparatus called an oscilloscope. When the sound wave from a source, such as a tuning fork, enters the microphone, the oscilloscope draws the longitudinal sound wave as a transverse wave, which allows us to see features, such as the wave's amplitude and frequency, more easily. From the trace drawn on the screen, we can measure the time for one complete vibration, or one complete wave. This is called the time period of the wave, t. On the screen, the distance between peaks is 4 divisions. And one division is set up to 0.005 seconds. Then, the period is 4 times 0.005 to equal 0.02 seconds. We can then find the frequency of the sound, f, using the equation. Frequency equals 1 over period. So, frequency equals 1 over 0.02, which is 50 Hz. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.